let's jump into the next section, which is the auto-ionization of water. All right, so a reasonable question would be, if we're going to talk about the auto-ionization of water, reasonable question would be, what in the heck is auto-ionization? What are we talking about? Well, what we're talking about is tendency of water molecules to spontaneously split apart into a hydrogen ion and a hydroxide ion. So water molecules just sitting in a beaker, some number of them are going to break apart to produce H plus and hydroxide ions. So water molecules are acting in the Arrhenius definition, are acting as both an acid and a base. And we also saw that last time we looked at the Bronsted-Lowry definition, where a water molecule can be a proton donor or a proton acceptor. So water is amphoteric according to both of these models. Okay, so water molecules spontaneously split apart to give hydrogen and hydroxide ions, but this is an equilibrium process, so these two will also recombine to make water molecules. So this process is always in equilibrium, and we can write an equilibrium constant for this reaction by putting the product in the numerator and the reactants in the denominator. But because water is a liquid, remember when we're writing equilibrium constants, we don't include pure solids and pure liquids. So we'll move this up a little bit. So this is an equilibrium where K is equal to the concentration of hydrogen ions times concentration of hydroxide ions. And this is a constant which is equal to 10 to the minus 14 at 25 degrees Celsius. We'll talk a little bit about the temperature dependence of this equilibrium. But this is important, and this is one that you should know. And because we're going to have a lot of different equilibrium constants, acid dissociation constants, and base dissociation constants, we're at a point now where we need to start giving our constants special names. And so this one is usually written as K with a subscript W, which people call KW, which means the auto-ionization constant for water. All right, so this is a chemical reaction you should know. This is the equilibrium constant you need to know. Okay. Now, there's another way that we can write this. You remember when we talked about hydrogen ions, we said that hydrogen ions can be written either this way or that way, depending on whether we want to make explicit the fact that the hydrogen ions are going to be bound to a water molecule. Sometimes this is more convenient, sometimes this is more convenient. The same thing is true of this auto-ionization reaction. So we can also write it this way. So instead of just one water molecule, now we're going to include two water molecules. And if this water molecule hydrolyzes or ionizes, let's say, and splits apart, it can release a hydrogen ion which binds itself to this water molecule making H3O plus, and this one that has lost a hydrogen ion becomes hydroxide. So this is really the same reaction we had up there before, but now we've written it in kind of a Bronsted-Lowry model where you can explicitly see proton transfer from this water molecule to this water molecule. So this one is acting as the acid, and this one is acting as a base. Again, as we said before, demonstrating that water molecules are amphoteric. And we can write an equilibrium constant for this. Since there are two water molecules here, we write that as H2O squared. Okay. But again, because the water is a liquid, we'll omit that. So this is another way to write that equilibrium. And this is the same reaction written before. We're just writing the H plus in this H3O plus form instead of writing it as just H plus. But this describes the same reaction. So this also is Kw, and this also has a value of 10 to the minus 14. Okay? All right. Now, equilibrium constants in general are temperature dependent. Okay. And Kw is no different. So if we look at the equilibrium constant as a function of temperature, at 25 degrees Celsius, Kw is 10 to the minus 14. I'm going to put something else over here. We haven't talked about this yet, but we'll talk about a lot of things with this P indicator in front of it. And P means negative log of something. So if Kw is 10 to the minus 14, the log of 10 to the minus 14 is just negative 14. But pKw is negative log, so that's 14. Okay. We'll see how that works out later. Okay. All right, but going back to this table, at 0 degrees Celsius, this is about 1.1 times 10 to the minus 15. And at 50 degrees, it's about 5.5 times 10 to the minus 14. All right, so I wanted to put this up. You don't need to know these values, except of course, as I said last time, you do need to know this set of values. I put the other ones up here mostly just because a lot of textbooks make a big deal out of this, and they ask you to calculate the pH of a solution at 20 degrees or calculate the pH of a solution at 50 degrees. There's some problems like that in the textbook. Perfectly fine study problems, but it's not something that I'm particularly fixated on. Some chemistry teachers really find this to be really important, and so it shows up a lot. They make a big deal out of it in textbooks, and it shows up a lot in standardized exams like the MCAT and other things like that. They'll ask you if pKw is the same at all temperatures or things like that. So I just wanted to point this out, mention that this equilibrium constant is temperature dependent, and not only is it temperature dependent, I mean it varies by a factor of 1,000, no, a factor of 100 at least, from 0 to 75, right? So it is a fairly significant temperature dependence, but unless it says otherwise, unless a problem specifically gives you a kW value that's different from this, you can always assume that we're working at 25 degrees Celsius, and you can always use kW equals 10 to the minus 14. Okay? All right. So let's see how we would use that. All right, I'm trying to write large enough so that you can see well, but just in case, what this says is, what is the concentration of hydrogen ions in a solution that is 0.15 molar sodium hydroxide? All right, so the first thing we have to look at is, if the solution is 0.15 molar sodium hydroxide, what does that mean for the hydroxide concentration? And you remember that sodium hydroxide is a completely soluble ionic compound. So when you put sodium hydroxide in water, it's going to break apart completely to sodium ions and hydroxide ions. And so every 1 mole of sodium hydroxide is going to give you 1 mole of hydroxide ions. So if the concentration of sodium hydroxide is 0.15 molar, that means that the concentration of hydroxide in that solution is going to be 0.15 molar. All right. Okay. But we want to know what the hydrogen ion concentration is. Okay? So in order to do that, we recall the equation that we had before. Kw is concentration of hydrogen ion times the hydroxide ion concentration. Okay. And we want to solve for H plus. So we can do a little bit of algebra, just divide both sides by OH minus. That gives us that. And just come over here a little bit. The hydroxide concentration. Okay. Since we didn't say anything about temperature, we can assume that we are at 25 degrees Celsius. So Kw is going to be 10 to the minus 14. And the hydroxide concentration, is going to be 0.15 molar. So we just put this in our calculator, see what we get. And I got 6.7 times 10 to the minus 14 is the hydrogen ion concentration. Okay, all right. So using this relationship here, anytime we've got the hydroxide ion concentration, we can calculate the H plus concentration. Okay. Also, anytime we've got the H plus concentration, we can calculate the hydroxide ion concentration. It works both ways. We just have to do the algebra a little bit differently right here in this spot. Okay, but if you've got this equation, you can always interconvert, I guess if you want to use that word, between the hydroxide concentration and the hydrogen ion concentration. So you should practice that, make sure you are efficient at doing that. That's a simple and important calculation for this section. All right. All right. So based on these concentrations of hydroxide ion and hydrogen ion concentration, chemists have defined the pH scale. And let me show you what we mean by that. So the concentrations of hydrogen ions and hydroxide ions can vary over a very wide range in aqueous solutions. For example, a solution of concentrated hydrochloric acid, right, that you might get out of the stockroom, is 12 molar hydrochloric acid. So the concentration of H plus is going to be 12 molar. Let's round that to about 10 molar. And if you do the math, you'll see that the concentration of hydroxide is going to be about 10 to the minus 15 molar. In neutral water, the concentration of hydrogen ions is 10 to the minus 7, and the concentration of hydroxide ions is also 10 to the minus 7. Okay. Notice when you multiply these two together, you get 10 to the minus 14. All right. And in concentrated sodium hydroxide, again, the super concentrated solution you get from the stockroom, it's so concentrated, it's almost kind of syrupy. It's very, very thick. The concentration of sodium hydroxide or hydroxide ions is about 10 molar, and so the concentration of H plus is around 10 to the minus 15 molar. All right, so what this means is that in aqueous solutions, the concentration of hydrogen ions and the concentration of hydroxide ions varies by a factor of about 10 to the 16, which is, good grief, like a billion or something like that. It is a heck of a lot of variation between these two. So chemists came up with a way to simplify this a little bit and describe this wide range of concentrations using a simpler number system. And that simpler number system is the pH scale. pH pH is defined as the negative base 10 logarithm of the hydrogen ion concentration. Okay, this of course has units of molarity, but the pH is unitless. Okay. All right, and similarly, we can define the pOH as negative log of the hydroxide ion concentration. What this does by taking the logs here is it condenses that range of concentrations from 10 to 10 to the minus 15, that huge range of concentrations, and converts that to a simple number between about 0 and 14 typically. Okay, so back to these definitions. pH is negative log of the hydrogen ion concentration. pOH is negative log of the hydroxide ion concentration. We'll sometimes use this. pKw is just negative log of Kw, negative log of that auto-ionization constant. Okay. And in fact, this notation is used quite a lot in chemistry. And in general, Px means negative log of x. Whatever this thing is, P of that just means negative log of that. And again, it's just a way of compressing a wide scale into a more manageable numerical scale. Okay. All right. So, how this applies to aqueous solutions. If we have a solution in which that's neutral, where the hydrogen ion concentration is equal to the hydroxide ion concentration, then both of those are going to be 10 to the minus 7. Okay. So that means the pH is 7. And we say that the solution is neutral. If the concentration of hydrogen ions is greater than the concentration of hydroxide ions, then the concentration of H plus concentration of H plus is going to be greater than negative 7. Okay. And the pH then will be less than 7 because of this, because of the negative sign in the log definition. Okay. And so for a solution in which the pH is less than 7, we say the solution is acidic because there's more H plus than hydroxide ions. And conversely, the last one, you can guess where we're going with this. If the concentration of H plus is less than the concentration of hydroxide, then the concentration of H plus is going to be less than 10 to the 7th. pH is going to be greater than 7. And when that's the case, we say that the solution is either basic or alkaline. I think most people say basic. I certainly say the solution is basic. Alkaline's maybe an older word. You'll see that a lot in the textbooks and things, but most people I know typically say the solution is basic. The pH is greater than 7. All right. All right, so there's one more log equation that I want to show you here. Okay. And, well, two things. Let me put this in here. All right. So remember, P of anything is negative log of that thing. So pKw is negative log of 10 to the minus 14. Therefore, pKw is 14. Okay, that turns out to be useful sometimes. Okay. Now I want to take the same thing though, and remember, I guess I'll put it here. Remember that Kw is the product of the hydrogen ion concentration and the hydroxide ion concentration. I want to write this way and apply the same log definition to that equation, because that's going to give us something useful. So change the order of the equation just to switch it to the other side. It's a little bit more convenient that way. If we take this equation, definition of Kw, and take the log of both sides, when you take the log of a product, you get the sum of the logs. So this is log of H plus plus log of OH minus. Gives us the log of Kw. Okay. Now, if I take this and multiply by -1, I get negative log of H plus negative log of OH minus equals negative log of Kw. But we know that negative log of H plus is just the pH, and negative log of OH minus is POH. And as we just saw, let me do this way. Okay. And pKa, we saw before, is 14. So that tells us that for any aqueous solution, again, this is based on the assumption that the solution is at 25 degrees Celsius. For any solution at 25 degrees Celsius, the sum of the pH and the POH has got to be 14. Okay. So this is also an important and useful equation. Okay. All right. When we summarize the equations that we have now in order to that we use to describe pH. Okay, so we got that one. So we've got these four basic equations for describing the relationship between these variables. I want to take these two in the middle and rewrite them a little bit, because these are easy. This one and this one are both easy to work with algebraically. For this one, working with this algebraically involves a little bit of log math. So I'm going to go ahead and do that. If you've got the H plus concentration and you want to calculate the pH, this is pretty straightforward. But if you've got the pH and you want to calculate the H plus concentration, that's a little bit trickier. So the way you would rearrange that is the hydrogen ion concentration equals 10 to the minus pH. And the same thing here. The hydroxide ion concentration equals 10 to the minus POH. Okay. All right. All right. So that's a summary of the equations we have describing hydrogen ion relationship between H plus and OH and pH and POH, relating all of these different variables together. Okay. All right, now I'm going to put these in a little table, little diagram. I like to call this the wheel of acidity. And the wheel of acidity, this is not the wheel. This is, I just want to point some out before I draw it. We've got these four different variables that we need to be able to define. And if you're given any one of these four, you should be able to calculate the values of the other three. And that's how this wheel of acidity works. Okay. So we'll start with H plus. Put hydroxide over here. So if you've got the H plus concentration and you want the hydroxide ion concentration, you can use this relationship here, that Kw, which is 10 to the minus 14, is concentration of H plus times concentration of hydroxide. If you've got, now let's go ahead and go this way. Once you've got the hydroxide concentration, it's easy to calculate the POH. Because the POH is just negative log of the hydroxide concentration. And from the POH, it's easy to calculate the pH because the pH plus the POH equals 14. Okay? So this allows you to convert from POH to pH. Okay? And once you've got the pH, you can calculate the hydrogen ion concentration. Because remember, concentration of H plus is just 10 to the minus pH. Okay. So if you're given any one of these, you can go around the circle to get the other three. If you've got this, you can calculate the POH, from that calculate the pH, from that calculate the H plus. If you are given the pH, you can use that to calculate H plus. use that to calculate OH minus, use that to calculate the POH. Okay. But here's the other thing. And well, let me say one other thing. If you're given the H plus and you're asked to calculate these other three variables, what I always tell people to do is start with the H plus, calculate the hydroxide concentration, from that calculate the POH, from that calculate the pH, and even though you're done, right, that's all the problem asks of you, I would take the pH that you calculate and use that to calculate the H plus and see if you end up with the same thing you started with, okay? If you go, you should be able to go all the way around this wheel, no matter where you start, come back to the same thing and get the exact same number, well, to within rounding error, get almost the exact same number that you started with. If you start with some value for H plus, come around the wheel, come back up here to H plus, get a different value, that means you made a mistake somewhere in your calculations. You need to go back and try again and find your mistake. That's the first thing about the magic wheel of acidity. Okay? The other thing about the wheel of acidity is that I've drawn this clockwise, but it doesn't have to be clockwise. You can go the other way. If you've got the H plus concentration, you can calculate the pH using that equation. And from the pH, you can calculate the POH, again, using the same equation. That's easy to rearrange algebraically. From the POH, you can calculate the hydroxide concentration using this algebraically kind of rearranged variant of that, where the hydroxide concentration is 10 to the minus POH. And from the hydroxide ion concentration, you go back to the H plus concentration using this. Okay. All right. So now, if you've got any solution, let's say you're given the hydroxide ion concentration, you should be able to use that to calculate the POH, the pH, H plus, come back here, get the same value you started with. You should also be able to take that value, go back to H plus, pH, POH, and then to OH, and see if you get the same value you started with. Okay. So, although there are practice problems, we're going to do one here in just a minute, and there are lots of practice problems in the book, in the study guides, you could make up your own problem if you want. You could say H plus concentration equals 1.6 times 10 to the minus 4 molar. Based on that value, calculate the other three values, come back and calculate H plus, see if you get 1.6 times 10 to the minus 4. Then take that 1.6 times 10 to the minus 4, go around the wheel the other direction, see if you get back up to the top with the same value. And then take another one and say, okay, the POH of a solution is 3.1. Go around the wheel one direction, then go around the wheel the other direction. You can make up your own problems and check them based on whether or not you get the same value when you complete the circle, and make sure you get the same value going both directions. If you can do that, then you've got it nailed. You've got it down. All right. Let's just do one of these. All right. Okay, so here's a simple problem. A solution has a hydrogen ion concentration of 3.15 times 10 to the minus 4 molar. just in case my handwriting's a little bit tough to make out up here. All right, what are the pH, pOH, and hydroxide ion concentrations in that solution? And then, is the solution acidic, basic, or neutral? All right. So I'm going to go for this one. Like I said, it doesn't really matter. I'm going to go around the solution counterclockwise in this case. Okay. So the first question is, what is the pH? That's just a simple definition. pH is negative, oops, should be simple if you do it right. pH is negative log of the hydrogen ion concentration So the pH is pH is just negative log of 3.15 times 10 to the minus 4. So our pH is 3.5. Let me put all of our variables here. All right, so pH is 3.5. Next, we go around the circle, calculate the pOH. pH plus pOH is 14. Therefore, pOH is 14 minus pH. Looks like about 10 and a half. Yep. All right, so our pOH is 10.50. Now we want to calculate the hydroxide concentration. All right. And I'm going to go ahead and write this here. This is really the definition. Okay. But when you do the algebra to this, and again, this is the part that's a little bit tricky. The algebra here tells you that the hydroxide ion concentration is 10 to the minus pOH. So hydroxide is 10 to the minus 10.50. You'll need to do that in your calculator, obviously. And I got 3.17. I got 3.175. I'm going to put that 5 there as a small subscript. Just as a reminder. If it was 3.171, I wouldn't worry about it too much. But because it's a 5, I'm going to keep that in so I don't introduce too much rounding error. So 3.17 times 10 to the minus 11 And then our last step, let's go back up here and check. We've got this relationship, so hydrogen ion concentration is Kw divided by the hydroxide concentration, which is 10 to the minus 14. I'm putting that 5 in there, like I said before, just to avoid too much rounding error. And ta-da, yay, we got 3.15 times 10 minus 4, which is what we started with. If we left that 5 out, you'd have a little bit of rounding error there, but it still would have been pretty close. All right, fantastic. I'm not going to do this now because I think you got the gist of everything, but you might, when you finish this, first thing you might do is take this 3.15 times 10 minus 4 molar and try going around that circle in the other direction and see if you get the same result. That'll be a great way to start your practice. All right, fantastic. Thank you all for sticking with me through that. I think we covered a lot of really good stuff, and we'll be back. What's the next thing? I think the next thing we're going to look at is strong acids. So we'll be back with that in our next video. Until then, I'll see you later. Thanks, everyone.